All right. Can you see that? You can.
Yes, we can.
All right. Hi, I'm Joshua, and I am a master's student at the University of Auckland. This is my first time doing a scientific presentation, so let's see how it goes. My project is called membrane-coupled Helmholtz resonators for mass suppression. Now, the motivation. New Zealand has a growing population, and as it grows, the infrastructure necessarily has to grow with it. But unfortunately, the infrastructure can encroach on urban areas such as this motorway here in Christchurch. And as you can see, there are houses nearby. Now, this picture was taken before the motorway opened, but since opening, there have been many residents who have complained about constant road noise and how it's negatively impacting their sleep and therefore their well-being. On that topic of well-being, it has been shown that noise pollution can have adverse effects on people's health, such as heart disease, elevated blood pressure, that's just to name two of them. And the frequencies of interest with all of these health effects occur are low end frequencies, so 500 hertz and below. And of particular interest to this project is the mass resonance. Now, mass resonance is problematic in households because it can be thought of as being built into the walls, if that makes sense. So the walls act as the masses and the air in between them acts as the spring. And this results in transmission of acoustic energy from one panel to the other. And of course, in the case of a household, it's acoustic energy transmitted from the outside panel through to the inside and then into the house. So the main focus of the project is to target this mass resonance frequency. Now, there are some existing solutions, such as absorption material like fiberglass, polyester, or pink fat as shown here, or you can use acoustic resonators such as Helmholtz resonators. And the project focuses on using Helmholtz resonators because their advantages are twofold. The first reason is that unlike absorption material, which provides very little improvement to sound transmission loss at low frequencies, Helmholtz resonators can reach those frequencies, and they can do so because of the second reason, i.e., they can be tuned to the frequency at which you want to improve the STL, and in this case, like I said, it's the mass resonance. So just a short, brief overview of Helmholtz resonators. A mechanism that are made up of two volumes, a larger volume and a smaller volume. The whole system can be a smaller volume, the neck, the larger volume, the cavity. And the whole system can be analyzed as a mass spring system, where the air in the neck can be thought of as the mass, and the air in the cavity can be thought of as the spring. And thinking of it this way and analyzing it this way, you can derive the Helmholtz resonance frequency equation, which I've shown on the bottom right there. And that was used extensively throughout the project to design the resonators. Now, conventional resonators, what I mean by that is like the rigid ones, I'll call them rigid, take up a lot of space. And a focus of the project was to use membranes and couple them to existing Helmholtz resonators to alter their dimensions. Membranes have been found to allow for decreased Helmholtz resonator volume. However, you're still able to maintain the desired frequency. This allows for better utilization of space in the wall, also being able to fit more resonators in the wall, which overall results in improved sound transmission loss performance. Now, preliminary tests were done to investigate the limits of this advantage that the membranes provide. And to do that, A rigid Helmholtz resonator was tuned to 190 hertz, the frequency that is within the adverse effect, the frequency to have adverse effects on human health. And then the membrane Helmholtz resonator was also tuned to that same frequency. And in both cases, the method of tuning was to change the volume of the cavity, primarily by changing the length, because when you look to build them for, say, PVC, it's much easier to change the length than to change, say, something like the diameter. The results of the simulation here show that to obtain 190 hertz for the rigid Helmholtz resonator, the cavity height is 98 millimeters, and it's 50 millimeters for the membrane Helmholtz resonator to obtain the same resonance frequency. Now, in effect, or in theory, this allows you to use two resonators, almost two resonators, when membrane Helmholtz resonators in the place of one. Again, allowing us to use more resonators in the wall to achieve greater sound transmission loss. Now, this use of membranes for targeting mass-to-mass suppression, for targeting the mass-to-mass or for mass-to-mass suppression, to my knowledge, hasn't been done yet, so that's a good thing for the project. Now, to test this, we 3D printed some resonators. So on the left there is the rigid one. On the right is the membrane coupled one. Both tested in an impedance tube using the standard that I've written down there. And so the results, here they are. And they show good agreement with the simulation results, where both of them are close to or at 190 hertz. So for the membrane Helmholtz resonator, it's 189, and for the rigid, it's 190. And they both exhibit similar sound transmission loss amplitude to the theory, so that's about 13, 14 decibels. So from this, the next step in the process was to make for a double wall, and then complete the comparison. But as you'll see in these results, the attenuation bandwidth is quite narrow, which isn't all that helpful, especially if you think of the mass-to-mass resonance, say it's at 100 hertz. There are frequencies on either side of that that still have adverse effect on human health. And I've put this sequence here because, as with most engineering challenges, the best solutions are often found in nature. And you can use the Fibonacci sequence, at least to some degree, or that kind of idea to some degree, to make a cluster of resonators that all have different sounds in order to, of course, increase the attenuation bandwidth. So for this project, the target frequencies ended up being 100, 110, 125, and 150. And like I said, the idea behind this is to put it into a double wall. So I just spent a little bit of time talking about the double wall side. It's important to think about the double wall and to keep its size in mind, because, like again here, I've got a double wall with two panels on either side of the chipboard, the frame in the middle, and this whole system will make up what I'm going to call the overall cavity. And then if you look at the image there, you'll see the frame is further divided into smaller cavities by the vertical studs, and these divisions are called individual cavities. And resonators are attached on either side of the cavity. So what this means is that within each of these individual cavities, these little blocks, we have resonators taking up a percentage of the volume, and this is called the fill ratio. Another way to think about it is the volume ratio that is filled by the resonators. For the testing wall, this came to 27% fill ratio, and this was based on things like spatial limitations, standardized material dimensions that were used to design the resonators. So from that, the theoretical cluster results are here, where each individual cavity is divided, consists of 12% of the 27%. 12% of it is made up of 100 hertz. 7% is made up of 110 hertz resonators. 5% is 15. 5% is 125 hertz, and 3% is 150 hertz. Or a different way to put it is, in each of those individual cavities, there were 8 100 hertz resonators, 6 of the 110s, 5 of the 125s, and 4 of the 150s. And the results here show the theoretical performance that is expected from the cluster. You can also see an orange line there, which has which depicts the mass-mass resonance frequency around 108 hertz, and that is why the frequencies are chosen to be what they were, to try and target that mass-mass resonance. So before I move on to the results, I'll just talk about the fabrication. So all the PVC pipes, so that's the cavities and the necks included, were cut using a drop saw, and the holes were drilled with a 25mm hole saw. The end caps stuck on the ends to eliminate any leakage, and the necks were fastened onto where the neck hole has been drilled using plasticine. This was to eliminate leakage, but also to increase reusability for future experiments. And here's an example of one of the completed resonators, the rigid Helmholtz resonators. And this one here happens to be the 100 hertz one. Now, cluster testing. Each of the segments were taped together and attached to the studs, as I mentioned before, adhering still to that 12, 7, 5, and 3%. And in the test, there was no absorption material. However, it can be put in between the resonators there for a different test. And this test was carried out in third octaves. And for the results, they show good agreement with the theory. And I've tried to draw I've drawn a black circle there to try and draw attention to where the cluster has done its job, as it were, successfully increasing the sound transmission loss at the target frequency range, and more importantly, or I guess as importantly, the increase in sound transmission loss at the mass resonance frequency, which again was the aim of the project. Now, as for next steps, it is to fabricate the membrane Helmholtz resonators. There are enough PVC pipes already. However, the membranes that is one of the next steps. And then after that, it is to do some parametric studies to see, or to investigate how varying membrane thickness affects transmission loss using different material, perhaps. And then optimizing the fill ratio of the resonators to try and obtain the highest transmission loss possible at that mass resonance frequency. Thank you for listening. Oh, sorry, still on mute.
Sorry, do we have any questions from the audience in relation to the talk?